Hi Physics 111. So this is part 6 of our chapters 5 and 6 videos. We had 5 in the first week. We're going to do at least this one and maybe another one. Depends on how timing goes, so we'll see. Today I want to start with another example of a static friction problem. So I did a couple of examples. One example earlier in a recorded video, and then we've done several in class. We might do some more this week in class, we'll see. But I wanted to do another one because this is a little different. Here we're going to have friction working in a vertical way, not horizontally or even down a ramp. So I wanted to do that specifically. So in this problem, this is number 19 from chapter 6, it tells us that we have a 12 Newton horizontal force. That's this F. And so it's 12 Newtons, and it's pushing this block into or next to a vertical wall. So it's pushing into the wall. It's not going through the wall. And it's not going through the wall, right? Because the wall itself is a surface, and so there's a normal that's being exerted. And then it tells us that the block itself weighs 5 newtons. Remember then when it says it weighs 5 newtons, that means that mg is 5 newtons. Not m. M is not 5 kilograms, right? M would be 5 newtons divided by g if we wanted to actually figure out the mass. Tells us the coefficient of static friction between the wall and the block is 0.6, which is pretty high, and the coefficient of kinetic friction is 0.4. Assume that the block is not moving initially, and then the first thing is it just says, well, does the block move? And then in unit vector notation, what is the force on the block from the wall? So let's go ahead and we'll draw our free body diagram. So here I'm going to draw my surface, right, which is my wall, and then I'll draw my box. And I'm following my rules for forces. Let me pause and bring that up. Okay, so I'm following my rules for forces. I just drew a box dot circle to represent my object. Now I'm going to draw the arrows for the forces. So I know there's a force this way, which we'll just call F, but we know that F is equal to 12 newtons. And because this is a surface, this wall, I know there's also a normal force, and the normal force is perpendicular to the wall, away from the wall. Now this object has a weight, and so its weight should act straight down, right? It's going to act vertically downward, and the amount of that is mg. And then there's static friction, or there's friction. And so friction is acting up. And so at first I'll just say, is this enough? So I'm going to put in Fs max, or Fs. How much does Fs have to be to not have it move? Right? To not have it move. So then that means I've got Fs. It means A sub y is 0 and A sub x is 0. And I kind of jumped the gun a little bit there. I should have already said, well, I want positive y to be up. And I'll choose positive x to be to the right. It doesn't really make any difference. Again, you can always choose different directions. You'll end up with the same equations at the end. And just basically choosing the opposite direction as your positive multiplies both sides of your equation by a -1. Well, that's the same equation. You just have everything multiplied by a -1. But you can unmultiply. You can then go back and multiply your equation by -1 again. Or as long as you multiply both sides by anything, it's the same equation. All right, so if I do F nets here, my F net x is F minus the normal force equals MAX, where A sub x is 0. And so I get that the normal force is just equal to the F. Well, in that case, here it's 12 newtons. All right. Then if I do the F net y, I get that the static friction force is going to have, when I subtract the gravitational force, if I want this to not move so that A sub y is 0, then the static friction force has to be equal to mg. When the static friction force, the maximum value that it can be, right? So this is our 5 newtons. The maximum value that it can be is mu sub s times the normal force. Well, mu sub s, according to our problem, is 0.6. And the normal force is 12 newtons. Well, that's only 7.2 newtons. So the maximum that we can get from the static is 7.2 newtons. So F sub s can be equal to 5 newtons, and then the block won't move, right? All we need is for S of s to be 5 newtons. It can go all the way up to 7.2 newtons, but it doesn't have to. mg is only pulling down with 5 newtons, so F sub s will only push back with 5 newtons. That's well within the capabilities of this normal force in this F sub s maximum. So we can totally hold up this block without it moving. So the block will not move. In unit vector notation, what is the force of the block on the wall? And that's another reason I wanted to do this problem. So part B, the force from the wall onto the block. Technically, this is both the force that we think of, the 12 newtons, which is acting in the I direction, but it's also this 5 newtons, the static friction force is being exerted by the wall onto the block, or it's an interaction force between the block and the wall. And so this includes F sub s. So if it's 12 newtons, we have 12 newtons from this F, and then we have 5 more newtons moving upward in J. So in unit vector notation, we have this, which is the F. Oh, sorry, never mind. Actually, that's not the F, right? It's negative. This is the normal force. The normal force is coming from the wall. And then the static friction force is also coming from the wall. And so we have a negative 12 newtons coming from our normal force. And we have a positive 5 newtons J coming from the static friction force. Hopefully that makes sense. Right, this little F is the F and normal is the response to the F going into the wall. Okay, hopefully if we have any questions on friction, we can go over that in class before we take the quiz on Thursday. But I want to go ahead and move into uniform circular motion from a forces point of view. So we talked about uniform circular motion back in chapter 4. We said that, chapter 4, we said that if an object is moving in a uniform circular motion, that means that they have an acceleration where the acceleration magnitude, a sub c's magnitude, is the speed squared divided by the radius of the circle. Remember, uniform circular motion means that the object is moving with a constant v, a constant speed on a circular path. It doesn't have to be the whole circle. Again, it can be just part of the circle with some radius r. So the circular path has a radius r. And the direction of the acceleration, the direction is always towards the center of the circle. So I've sort of drawn a little cartoon here again. If you have some mass at this location and it's moving around in this circular path, at that time it's going to have a velocity which is tangent to the circle, and the direction of the acceleration is directly towards the center of the circle. And the amount of that acceleration is going to be this speed squared divided by the radius. But some force has got to be causing this. In fact, it's the net force in that dimension. Some net force has got to be causing this acceleration. And so what we would say is that the net force, Newton's second law, becomes the net force is mac, because that's the acceleration this object actually has. So it's almost like we were given the acceleration, like in earlier problems where I might have said, I know the elevator is accelerating at 1.5 meters per second squared up. That is a given of the acceleration. And when you go through, when you do your F net equals ma, you knew the a. Here we also know the a. If we know something's moving around in a circle, then we know the speed and we know the radius, then we know the a. And we know the direction of it as well. Now this is just the F net in the dimension that has the AC. So this object here is moving around in a circle as we look at it from this dimension, but it could be that if we looked from the bottom, if we looked at this, might also have some gravitational force moving perpendicular, say, into this board. Maybe they were looking at this circle from the top or something. And so we could have another dimension that has forces, but in this dimension, as we're looking at it here, it has some acceleration at that instant towards the center of the circle. So I was going to do a couple of examples here. We'll do a Ferris wheel. So this is a lot like number 47 that y'all are supposed to do for practice. And so we say there's a girl riding a Ferris wheel. She has a mass of 40 kilograms. The radius of the Ferris wheel, of the whole thing, is 8 meters, and the speed that everybody's moving around is 5 meters per second. And I want to know, at the bottom of the ride, what is the normal force on this girl? So I'm trying to show this little cartoon here. So she's at the bottom of the ride, and here she is riding in the cart. And there's a normal force from the cart's floor pushing up on her, right? There's a normal force. And so we're going to see what this looks like. So let's go ahead and do a free body diagram for this girl. So the box is the girl, not the thing that she's riding in, but the box is the girl. So she has gravity. She has her gravity pulling down on her. But she's inside this chair or something that she's sitting on, and it's pushing up with a normal force, right? Now that's really all that's touching her, right? Gravity can pull on her without having to touch her, and then the box is pretty much the only thing that's really touching her, and so it's the only thing that's exerting a force. So there's a normal force being exerted on her. I'll go ahead and say positive y is up. Now acceleration, she's at the bottom of this circle, and so she's moving around. So according to my rules above here, she's got an acceleration at that instant which is upward, and that acceleration is this a sub c, and so we'll write that over here as well. There's an a sub c, which is her acceleration, which is v squared over r. And so when I do my F net equation, I only need to do F net y. I get the normal force minus mg equals m a sub y, but a sub y is a sub c, and a sub c is v squared over r. And so I have that the normal force minus mg equals mv squared over r. And so to get the normal force, I move this around, I get mg plus mv squared over r. And I'm going to do a little bit of difference here. I'm going to say I'm going to take that out, and I'm going to calculate this amount. So v squared, v was 5 meters per second, and the r was 8 meters. So I'll write it out actually. 9.8 meters per second squared plus v squared is 25 meters squared per second squared divided by 8 meters. So that's 9.8 plus 25 divided by 8 is 12.925 meters per second squared times her mass, which was 40. Which is 517 newtons. Sometimes you'll hear people talk about pulling how many G's, a multiple G, 2 G's or 3 G's or 4 G's. This right here, right, when you're at the bottom of these things, if the faster you're moving on a ride like this, when you get to the bottom, you feel that force that the floor has to push up on you on, right? You feel like you're pushing into the floor more. What that really means is the floor is pushing back on you, and it's a sign that you're pulling more than 1 G. So this is actually, if we wanted to say how many G's that was, we'd say 12.925 divided by 9.8. Right? So this, oh my goodness, 12.925 divided by 9.8 is 1.32 G's. Yeah, that's how many times it is. How much times gravity it is. You don't have to do that, but just as an example of what this is talking about. How about when she's on the top of the Ferris wheel? So now if instead of being at the bottom of the Ferris wheel, she's up here, right, at the top of the Ferris wheel. Again, we can do free body diagrams. We'll still have, gravity doesn't get to change its direction. Gravity's still down, and normal force is still up. And I'll go ahead and I'll say positive y is up. But now, if she's at the top of this Ferris wheel, then the acceleration that she feels is downward. Right? Her acceleration is actually downward by v squared over r. So when I do F net y, I'll still get that the normal force is up, gravity is down, this equals mass, but now this is negative AC. AC is in the negative direction, and so I have to explicitly put that in there as a negative. So I get that the normal force minus gravity is equal to negative m v squared over r, or the normal force is gravity's, or force of gravity, subtract mv squared over r. So I had an increase in the gravitational force, or in the limitation of the normal force that I had to have at the bottom. Now I'm going to have a decrease. So now I'll have 9.8 subtract 25 divided by 8. And I only end up with mass times 6.675 meters per second squared. And in fact, the amount that I have too much up here at the top plus v squared over r, that's the amount I have too little compared to gravity. When I'm at the, when I'm at the bottom, I have too much-ish, and when I'm at the top, I have too little, and it's the same amount. It's just you're adding it when you're at the bottom of the Ferris wheel and you're subtracting when you're at top. And it is possible that you move so fast on a ride that when you get to the top, there's no need for a normal force at all. Or at least there's no need for a normal force to push up on you. Sometimes you've ridden on a ride and you actually will fly almost out of the cart, right? And then at that point, the lap bar is actually holding you down. Then a normal force actually has to help push you down to keep you in the ride. If you move fast enough, if v squared over r is large enough, then you could conceivably not have enough force from gravity to hold you in. You'll need an additional force to help keep you from flying out. All right, let me do another classic example of curved motion. This is a car on a curved road. Again, it doesn't have to go, you don't have to go all the way around a whole circle for this to occur. You can do just part of a circle. So if we have some road and we have our car traveling along it and it's a straight road and then the road starts to curve, what happens at that point? So I'm going to go ahead and do it. We're going to finish this up in this video so that we're done. Okay, so here's my car, and again, I've got a velocity which is a tangent to the road here. I've got a mass of my car, and I have a coefficient of static friction, and it is static friction that actually keeps the car on this curve. So if I look at the car, I'm looking at it here, this is an overhead view, but really to look at the forces, I need to look from the side. Although I can say that this is the direction of A sub C, right? It's coming off this left-hand side. If I looked at it from the rear, and that's what I'm going to do right here. If I look at it from the rear, so this is supposed to be an eyeball looking at it from the rear, then the acceleration is moving off to the left. So here's my acceleration, where again, that should be v squared over r. So this is my car, looking at it from the rear, so that the velocity is into this sheet or the screen for the car. And these are my tires, and here's the road. I definitely have gravity acting down. Mass of my car times gravity acting down. The road will exert a normal force. And then, let me actually move this slightly over. There's also a force between the tires and the road. And the direction of that force is this way. And that is the static friction force. And let's say that we're using the maximum static friction. So I want to know, what is the maximum speed the car can go around this curve? If it's the maximum speed, then that means I want to know the maximum static friction force. And it's a static friction force because in this dimension here, the car is not moving. It's not moving further away from the center of this circle, and it's not moving closer to the center of the circle. It's staying a set radius away from the center of the circle. And so it's not moving in this dimension, which we will call, I'll go ahead and call that positive x and straight up positive y. Here, we aren't expecting this car to bounce up and down off the road, and so A sub y is 0. Okay, so if I do F net y, I have the normal force minus mg equals may. Now, don't ever forget that you have to do equals may and then go look at what you've said about the acceleration. So the normal force here is just mg, which I could calculate if I have the mass, but I'm going to hold off on that for a second. F net x, here I've got positive x this direction. I only have one force, the maximum static friction force. And that has to equal the mass times the acceleration, which is also in that direction, which is a sub c, or is v squared over r. And this is really the maximum speed that I'm trying to find here. Static friction force max is mu sub s times the normal force. So mu sub s, I had as a given, was 0.300. Actually, let me do my algebra first, and then I'll come back and I'll plug in numbers if we want to. So moving this all around, I can write that V max, if mu sub static friction force is, well, I'll leave it in there. So we'll say this is going to be R times the maximum static friction divided by m, take the square root. But the static friction force is mu sub s times the normal force, but the normal force is mg. And so it doesn't actually matter the mass. V max is the square root of the static friction coefficient times r times g. And that's true. There's nothing here that's specific to this car. There's nothing here that's specific to this curve even. It's just basically saying that the speed that you can go around a curve on a road depends on how much friction is there. The more friction there is, the faster you can go. The larger the radius is, the larger this number is, the faster you can go. And if for some reason you could magically do this curve on a planet which had a larger gravitational force, the faster you could go. But it's not linear, it's a square root. So if you double the radius, that doesn't mean you can go twice the speed. It means you can only go the square root of 2 times the speed that you were going before, right? You'd have to make the radius 4 times as large to be able to go twice as fast on the curve. This is really similar to number 41. We can look at that really quickly. I'm not going to do it right now, but they're asking you about a cat on a carousel. It's the same physics here. Instead of a car on a curve, you've got a cat on a carousel, where they tell us the radius of a cat goes on a stationary merry-go-round in an amusement park. The radius of the merry-go-round is 5.4 meters from the center. That's where the cat is, at least. And then the operator turns on the rod and brings it up to its proper turning rate of 1 rotation every 6 seconds. So you do have to figure out what V is, right? For number 41, you do have to figure out what the V is. Remember that the speed is just going to be how far around did you go over how long did it take you to go one time around. So they tell you the radius and they tell you how long it takes, so you should be able to get the V. And then since you now know the V, so you know V, that still has to be equal to mu sub s, r, and g. So you're going to now figure out what does mu sub s have to be to allow this cat not to slide off the merry-go-round. All right, so that's all for chapter 5 and 6. And the next video is going to be on chapter 7. We're going to do a significant amount of chapter 7 and 8 this week.